used variation theory in a project that I worked on for quite a long time in South Africa. I'm not in South Africa anymore. I'm in Dublin. It is colder and wetter and grayer in terms of the variations that are standing out and screaming at me as I look out of my window. So some nice memories and some nice work. So I'd like a little traipse through some of how we've been using variation theory in that work. So a little biography to begin with, and it's a variation theory biography to kind of say where it is our work with variation theory comes from. So my first interaction with variation theory came via a project that was happening at WITS, and it was called the phenomenographic. I worked with who was in the WITS School of Education at the time, and as part of that project, I met Shirley Booth and Ulla Runesson, and a little while later down the line on a little trip to Sweden, met Ferenc Marton as well. And as part of that work, and as I was preparing for the work in that project, with no background in either phenomenography or variation theory, I read that book, Learning and Awareness. It's kind of the year dot or the Bible in some ways of where current work on variation theory began. And I liked the book, and I liked it almost immediately. Partly because it just seemed to have concepts which I found useful for thinking about mathematics teaching, and mathematics teacher education. Now, as that work went on, I found, as I was reading more and more of the papers, my bent went towards variation theory rather than its kind of parent theory in some ways, which is phenomenography. Because variation theory to me seemed to have more of the tools that I was looking at. It seemed to have more developmental possibilities and more analytic possibilities in relation to mathematics. So I kind of went down the variation theory route rather than more deeply into phenomenography, although I had begun with learning and awareness, which presented many phenomenographic studies. And in doing that work, my reading of variation theory expanded. And in particular, I was reading Ulla's work in this book, which I found really interesting. And then a book which I come back to time and time again because I find it so useful, which is Anne and John's work on the book that they wrote on maths as a constructive activity, learner generating examples. And much more recently, looking at a book which has talked quite a lot about the Chinese version of variation theory and how they've used it in Chinese traditions. So in some ways, I kind of in my head caricature this as a Swedish variation theory. I don't know if I think I call it Anne and John's variation theory rather than English variation theory, because it seems to be very much Anne and John's work. And then Chinese variation theory, which I've read more about and found very interesting more recently. Now, you've heard quite a lot about these three traditions in the 3 lectures that we've already had. And I'm going to talk a little bit about how I think I pulled on some of that work in the work that we did in South Africa. And one thing that followed on from this early reading was we had a colleague of Ulla's, Annalena Ekdahl, had come out to South Africa, and she actually did an adapted learning study intervention in one of the schools that we were working with in South Africa. And in her study, variation theory underpinned both the design of the intervention that she was working on and then the analysis of the data that came out from it. And I'll say a little bit more about some of that later on, but she wrote up her PhD in 2019 and had published papers from that study earlier on. So there's the thesis that she was working with. So that in some ways is a trace of my background in relation to variation theory and the work that I've read within variation theory. Now, I liked much of the work I've read, as I've already said, because what it seemed to present to me was some really nice options for thinking about mathematics and mathematics teaching, and in my work in mathematics teacher education as well. But what it seemed to me that a lot of the work was doing was giving me some lovely examples of what skillful, really skillful mathematics teaching could look like. People who thought quite deeply about the mathematics and how it came into play in mathematics teaching with some tools and concepts for thinking about what really good mathematics teaching could look like. But I also had a problem in some ways, a tension that I was working with, because I was working on the South African ground. And in the South African ground, some of that skill, some of the aspects that we would talk about as really as involving, as what underpins really skillful mathematics teaching, having a really strong sense of the rationales for the decisions that I make as a mathematics teacher, and a really strong sense of the trajectories that I might be working about in mathematics, seem often, not just in the work that I was doing with a team in South Africa, but in the other work that I was reading in South Africa, lots and lots of evidence that some of those skills and some of that background in skillful, the background knowledge about mathematics was absent or limited in much of the South African ground we were working in. So I'll come say a little bit about the South African context that we were working with, and it relates particularly to primary maths, although I'll make some references to problems which are more generic than primary maths as well. So in the South African context, if we think about learning, broad evidence on the ground that there are poor learning outcomes in mathematics at all levels. This isn't just primary, it extends well into secondary as well, and at school exit levels and beyond. So that there are poor learning outcomes in mathematics at all levels in the system. There are lags, and these have been written about, again, at multiple levels, but the most recent writing tends to show that there are lags on the specified curriculum, which are already in place by the end of grade 1. So, and this is now talking about significant proportions of children who are not meeting stipulated curriculum requirements by the end of grade 1. We already knew earlier on with certainly by matric, which is the end of school, the school leaving levels, and certainly at early high school levels, that there were problems there in relation to the specified curriculum. As more work has happened in primary, it's become clear that the roots of much of that lie actually in the early grades of primary level and primary schooling, and that there are lags. For the majority of children, we would say, very early in the primary schooling system. And a problem that's been written about widely within what makes progress difficult to make in early primary school is the evidence that there's lots of evidence that children are not moving on from that phrase, calculation by counting, to calculation by structuring. Now, by what I mean by calculation by counting is children repeatedly working with counting in ones, either by using marks on paper or by using their fingers and then toes and other people's fingers if they need to do early calculation problems, early addition, subtraction, multiplication, and division problems, rather than calculation by structuring. And what I mean by calculation by structuring is using the properties, the patterns in the number system to help work to do calculation more efficiently than counting in ones all the times. Now that's kind of a mouthful to say, but pictures demonstrate it really clearly. So here's one example that came from our early work with a master's student I was working with at the time, Marie Vates, who was looking at some of children's work on assessments in early primary school. So here's an example of a grade 2 learner who has got, you can see there, 2 questions done correctly, but you can see how the child has done them correctly. So 10 plus 10 plus 10 is answered correctly by making 10 marks and another 10 marks and another 10 marks and then counting them up to get 30. And then similarly for 10 minus 2 minus 2, again, a correct answer done by 10 tally marks, crossing out 2, crossing out another 2, and then counting the remaining. So you've got lots of evidence of early in the primary school, and this is early grade 2, where the children would be kind of 6, starting to turn 7, that children are working in these ways. Now you might say, well, early grade 2, that's not such a problem. But actually the trouble is that we've got lots of evidence that children are not moving on from these kinds of methods. So the next example I'm showing you here comes from grade 5. And Eric Scholar was an academic who did quite a lot of data collection across many of the South African provinces and repeatedly found examples like this. Now, by grade 5, you're talking about children who are 11 years old. They are working on double-digit, 2-digit multiplication. And this is an example of a page of a child trying to do 2-digit by 2-digit multiplication questions, something like 23 times 12, for example. And you can see that once again, what you've got is a group of 23 being drawn and circled, and another group of 23 and another group of 23. So you can see how long it might take to answer a question like 23 times 12 in this way, but also how easy it is to make an error. And what Eric Scholar reported on was significant proportions of children in grade 5, and he's actually got some data from grade 7 as well, to say that we've got large numbers of children who continue to work in this way, well beyond the number ranges where this is appropriate. And he provides figures to show that actually the best that he was seeing in grades 5 and grade 7 was working with multiplication and division by repeated addition or repeated subtraction. So you've got some progress for some children. You've got some children remaining in the counting, but the best that it's moving to is repeated addition, which remains actually a fairly inefficient way of working with multiplication and division. So that's kind of some of the ground. And what struck me about the contrast was the skillfulness that I was seeing in the variation theory literature and the phenomenography literature of examples of really lovely ways of working with mathematics, coupled with a ground in South Africa where we were seeing much, much more fundamental problems going on, and yet being interested in where the overlaps, where the points of intersection might be that could bring these quite interesting tools that I was seeing in variation theory together with the ground. Now, I've talked about learning, but there are also problems in the South African context when we look at teaching. So first off, there are, again, extensive writing that there are evidence that there are gaps in teachers' mathematical content knowledge, particularly at primary level, but the problems extend into secondary as well. And what's interesting about this work, because this is work that has international parallels, particularly at primary school, and when we talk about primary teachers who often are generalists. The thing in South Africa, and what marks some of the South African evidence, is that teachers, there is evidence that teachers struggle with the content they are teaching at the level of content knowledge and at pedagogical content knowledge. So this is not a horizon knowledge problem in the ways that Deborah Ball might talk about it, i.e. not understanding the span and what might follow primary mathematics teaching concepts. This is problems with the content they are teaching at the level of content knowledge and pedagogic content knowledge. And that evidence, much of it has been collected in the kind of the middle grades, which would be upper primary in the South African terrain. What we were seeing when we were going into the early grades classrooms, i.e. the lower primary grades, was problems not with teachers not being able to simply answer the questions that they were teaching. Rather, in the lower primary grades, it was problems with coherence and connection in the ways in which mathematics teaching was being taught. And again, I've got some examples that I can show you of what that looks like. So here's a little example that comes from a colleague's work. Corin Matthews did his PhD, and he was looking at division teaching in grades 3 and grade 4. And he saw some examples that looked like this. So a teacher would put up a task like 10 divided by 2 on the board, and then say, I'm going to show you how to do this. And she would begin by saying to the class, children, the first thing you've got to do is you've got to draw 5 big circles. And then she would say, well, we put 2 dots in each circle. What's our answer? Yes, it's 5. And sometimes there'd be a check to check that once you put the 2 dots in the circles, yeah, it's 2, 4, 6, 8, 10. Yes, so we've got the answer now to 10 divided by 2, and it's 5. Now, the problem that we were seeing there, which I'm sure many of you have seen as well, is that the question is 10 divided by 2, and the teacher's mediation of how to answer that question begins by dropping in the answer 5 into the ways in which she shows children how to answer that question. So in one way of thinking about that is that the what's unknown is being conflated with what's already known. So there were problems, and Corin wrote about this in terms of problems with coherence in the way mathematics is mediated. A different kind of problem that we were seeing earlier on in a project that I'll tell you a little bit about in a minute, where we were doing lots of classroom observation, was the disconnected treatment of examples. So we were in a lesson, again, I think in early grade 2, where a teacher said, the task in focus is I'd like you to give me 2 numbers that add up to make 16. And the children in the class who had cubes in front of them The first offer she got was 8 + 8 was offered, and the teacher wrote this on the board. And she said to the class, I'd like you to check that this works. And she did this at the front by counting out 8 bottle tops and getting a child to come up actually and count out 8 bottle tops and another 8 bottle tops and checking that it made 16. Following that, another example was offered and 10 + 6 is offered. This is again verified by making numbers on an abacus at the front of the board and counting. As the lesson proceeds, another 2 on numbers, and at one point 9 + 9 is offered. And the teacher asks the class to make 9 + 9 with their cubes and again check whether it makes 16. And if it doesn't make 16, the answer was rejected in this case. Now, there are several examples in this lesson, and each time there is a check back to empirical first principles verification by counting. And for example, with the 9 + 9, there's no reference back to the fact that 8 + 8 makes 16 has already been established. And can we reason our way into thinking whether 9 + 9 makes 8, 9 + 9 can make 16 or not? Similarly, when 9 + 7 is offered, she asks the class to check. Most of the children say 16, 17 is already heard as the answer, and the teacher asks the children again to check and count with one learner coming up to do that. So what we were seeing there was a repeated going back to first principles counting. And one of the ways in which we kind of characterized this teaching was a disconnected treatment of examples. Every example that comes up is treated as a new example where you begin from first principles again and again. And that was a phenomenon which we were seeing more widely as well. This is a particularly stark example, but we did see this kind of phenomena more broadly. And another example, again, which points to a slightly different kind of phenomena, 8 + 6 is the question put up on the board. The teacher has a large abacus that she's working with on the front, and the ways in which she uses this abacus to show 8 + 6 is she counts across 8 beads on the top row of the abacus. Now, the abacus, the typical abacus, is kind of marked out in rows of 10. And instead of filling in the 10 to show the +6, she counts 6 beads across on the second row, and then all the beads are counted in ones from 1 to get to 14 as the answer. So what we were saying about phenomena like this was we were seeing the beginnings of an availability of what we would call structured resources, resources that kind of are underpinned or underpinned by base 10 relations in this case. But the ways in which the teacher was mediating their use was in unstructured ways, i.e. not making any reference to base 10 structure by filling in the 10 or making use of base 10 thinking. And therefore not mediating for progression beyond counting again into calculating by structuring. And we were writing about phenomena like these in our early work in the project. So coming back and summarizing that, there are problems at both teaching and learning levels, which seemed, certainly on initial reading, quite distant from some of the lovely writing that I was reading about in variation theory. But one further problem that I will mention at the level of teaching, and this is writing that actually comes from Richard Tabulawa in Botswana. There's been lots of writing in Southern Africa where the first wave, certainly in South Africa, the first waves of reform were very much about promoting learner-centered pedagogies. And Richard Tabulawa, writing some 20 years after that, said, widespread evidence that in Southern Africa, traditional teacher-led whole class instruction predominates. Now, that's been written about widely across lots of pieces of writing in the Southern African region. But Richard Tabulawa, writing about this, says what he sees is a tissue-level rejection, almost a bodily rejection of learner-centered pedagogies. And his argument was that learner-centered pedagogies simply don't fit with the cultural norms of Southern Africa, both in the broader terrain and in terms of classrooms, where more authoritarian cultures predominate. Now, it's a point that I'm going to come back to when I talk about some of the interventions and the work with variation theory that we did. But fundamentally, for me, what I was seeing in this work was that there was a gap between the sophistication of the variation theory tasks examples and concepts that I was reading about in the literature and the realities of working in the South African ground. So the project that we were working in was an interesting one because it had some interesting terms that we were complying with. So there was an initiative that was launched in the late 2000s, 2009, 2010, where there were calls for these South African numeracy chairs. There were secondary chairs as well, and Jill Adler held one of the secondary chairs. But there were also calls for primary chairs, for primary mathematics chairs, and they were called numeracy chairs. And it was an initiative where a call was put out and people had to apply for them. And there was a very specific remit about how these chairs had to kind of play out. And part of the remit was that the chair was to partner in the project with 10 primary schools serving historically disadvantaged populations in South Africa. And the remit was to design, implement, and investigate research-based interventions for improving primary maths teaching and learning, essentially to deal with the kinds of issues that I've just kind of shown you on the previous slides. But beyond that, there was an interesting little stipulation which said produce research on sustainable and pragmatic solutions with the expectation that the interventions that we might trial in 10 schools have the potential to go at broader scale, to work at broader scale. And the ambition was very much to go at much broader scale, i.e. into provincial and national interventions. So very emphatically that there was a sense that these interventions had to be interventions that couldn't be run by a small group of skillful teachers. They had to be practical enough to go into a much broader ground. Now, at the end of 2010, 2 numeracy chairs were awarded in South Africa to begin in 2011. I held one of those at Wits University, and my colleague Melanie Graven was awarded the other one, and she was working at Rhodes University. These chairs were awarded with 5-year terms, which is a luxury because it kind of gives you a longitudinal window for intervention work. But they had an additional luxury, which we had the capacity at the end of the 5 years, there was an evaluation. And if the evaluation was positive, you got an extension into a further period of 5 years. And this actually happened twice. So the third 5-year iteration is now in play. So how did we work with variation theory in this project? Well, I think we worked with variation theory in kind of 2 ways. The first way, which I'm going to talk about less today, is that variation theory, we used it in the design of intervention materials. So I've kind of left some links up there and I can share the slides. So there was a multiplicative reasoning intervention, where Mike Askew led, again, a colleague, Mike Askew led in terms of the design of materials with our team. And we talked about the ways in which variation theory underpins some of the design of those materials. And particularly the way in which we were looking at variation theory there was those questions that I came across first in Anne Watson's work, which is that question about what varies and what stays the same, and asking teachers and children to attend to that in the design of examples. And through that and thinking about what's invariant is getting at getting teachers and children to recognize what essentially is it that makes a situation multiplicative. So the tasks, the examples, and the sequence of lessons that we developed were geared towards using variation theory in those ways. And a second project where we used variation theory was a project which was focused on mental mathematics in the early grades. And this is a project which is now in national rollout. So it was one that started in the smaller scale and has moved up into national rollout now. And in that project, what we did was we looked at multiple representations of mental mathematics situations and talking and seeing the generalized ways in which strategies could be used across those situations. And in particular, we were looking at strategies that make use of base 10 structure or number structure in those. So strategies focused on things like jump strategies, which is useful for 2-digit addition and subtraction, compensation-based strategies, and reordering, which is based on ideas like commutativity. So in that project, we think we've pulled out on things like conceptual and procedural variation, which you've heard a little bit about, I know, in the earlier lectures in this series. So that's one way in which we've used and worked with variation theory. But what I'm going to focus on today is the second arm of our work, of working with variation theory, And this is in terms of studying and supporting teaching. Now, I've said already that we had these projects where we were working longitudinally with schools over time. And one of the kind of empirical challenges that we had was kind of, how do we characterize and think about the changes in teaching that we might be seeing over time in the context of schools and teachers that we are working with, where interventions and professional development interventions have gone in? And we had, obviously there are kind of lots of ways in the international literature thinking about the quality of teaching and what's happening when teachers are mediating mathematics on the ground. But in much the same way that I've talked about some of the variation theory concepts we were working with, many of the international frameworks for looking at the quality of primary maths teaching also seem to us to be at some distance from the realities of the South African ground. So in some ways, it felt like we were reading about, I characterize, and this is perhaps a pejorative term, about champagne versions of theories. And we had kind of on the ground versions of those theories that we needed to develop if we were going to be able to disaggregate the more basic features of teaching and the kinds of changes in teaching in those more basic features that we were seeing on the ground in our work. And the more basic features of teaching that we were interested in, based on the challenges that I've already talked about, are things like coherence in teaching, connections, teachers making progression moves, and teachers making responsive moves to the kinds of things that they hear children say. So in the VIPS Maths Connect Primary project, which was the name of the project that we were working with, we were collecting over time video data on teaching. And the first spell of that was kind of going between 2011 and 2018. But I know Tony Essien, who's leading that project now, is still working on collecting and doing some video-based data collection of teaching now. So it is a kind of ongoing enterprise. And in the course of that work, we had lots of examples, lots of excerpts of observation-based data of classroom teaching. And what we were doing with that data, particularly as we were getting a few years in, was looking for what is similar and what is different across different excerpts of teaching, and trying to produce, as we looked across that work and trying to understand the differences in what we were seeing, was to try and produce a modest but still aspirational trajectory in terms of what developing teaching might look like, but one that was tailored to the context, conditions, and cultures of the ground that we were seeing in South Africa. And where we ended up with that work, something's got stuck. There we are. Was a trajectory that we built that seemed to go to us in this kind of this broad trajectory, that teaching that contained errors or incoherence, we were trying to support to move into coherence. And teaching that was starting to look coherent but not connected, we were starting to move into connected teaching. And as teaching started to get more connected, we were starting to want to build those connections into more powerful generalities, some more generalized ways of thinking about what powerful mathematics teaching could look like. So what did this work look like? So our focus was on how did it differ particularly from the international literature base? I think we were looking at a focus on how mathematics is mediated, and were much less interested in pedagogic forms like learner-centered approaches. Now, that was to do with being responsive to the ground and the cultures that I've already talked about. So a focus on how teachers essentially are working and mediating mathematics in classrooms. There was also, we thought, significant attention to how teachers orchestrate their mathematical working in terms of the ways in which they think about and work with tasks. And in terms of their work with tasks, we were particularly interested in teacher talk, the artifacts, and by artifacts, I mean the kind of manipulatives, the physical or the brought-in resources that they were using in class, and their inscriptions, which is essentially the written work that they were doing in class, or the annotating that they were doing in class. Those were kind of the hinges that we used to look at the quality of mathematics teaching. And we ended up in, after a few years of work with a framework that we found useful for thinking about the quality of mathematics teaching. Now, this framework, and I'm not going to go through all of this framework in any detail, we think is responsive to the ground. And the bit of it that I'm going to focus on today is particularly the parts that are underpinned by variation theory. But we were using this framework more broadly to kind of code for, to think about and characterize the quality of teaching and changes in the quality of teaching over time. And the methodology we used for this was when we were observing lessons, we would break the lessons into episodes that were directed by a focus on particular mathematical ideas. And when the idea changed or shifted in some way, that would mean the start of a new episode. And we coded at the episode level for the semiotic assembly that teachers were putting together across their work with artifacts and inscriptions and talk. And then the extent to which we could see that teaching was responsive and moving towards structure and generality. In terms of the theoretical basis of that work, we would say that probably the bias is towards an instructional focus. And we note that because some of the international frameworks are very much about learner agency and learner input, so classroom interaction. The nature of our classrooms, because they're so teacher-led, meant that we were looking quite a lot at what teachers were doing instructionally. The base has several theoretical features. So some of it is kind of a Vygotskian base, a sociocultural base in how we think about teaching and teachers' mediation of mathematics. There's also a basis in semiotics because we were looking at the semiotic bundle in terms of the different routes via which teachers mediated mathematics. But variation theory was always also in there, and that's the part that I'm going to talk about today. And as I've said already, we did include attention to responsive working in the classroom in terms of what teachers were doing. So I'm going to focus not on all of this, but two particular strands of this work where I think the variation theory parts come to play. So the methods for generating and validating solutions was one of the strands that we coded teaching for, and building mathematical connections was another strand. And in both of those strands, I'm going to share how we worked with variation theory. So here's the strand, which is about the methods that the teacher might communicate or validate if the method comes from a learner in the classroom, in terms of methods for generating or validating an offered method for solving a problem. I'll say a little bit more about why we could develop this strand, but you can see in this strand that at the lowest level of our coding, there would be an offer or an acceptance of a method. Either no method is offered or the method offered is problematic in some way. We then moved up, and you can see our next code is a singular method or a validation. And the kind of descriptor that we had for that the teacher would offer or accept a method that generates the immediate answer to the problem. And it might enable the production of answers in the immediate example space, but doesn't go more broadly than that. And you can see already we're picking up on variation theory ideas because the idea of example space is being used here. One level above that, we were talking about localized methods or validations. And here there would be a provision or an acceptance of a method that can generate answers beyond the particular example space, but it's not fully generalizable. And then at the top level, we had generalized methods or validations. And here there would be an offer or an acceptance of a strategy or method that could be generalized to both other example space and without restriction to particular artifacts or inscriptions, because that was one of the ways in which we saw that some of the offers we saw teachers make were limited. So here are some examples that we coded in different ways. We looked at the mediation of methods for solving problems, and these were considered, as I've already said, in relation to the example space that the methods could be applied to. And we thought about that pragmatically in mathematical progression terms, and I think the examples might help you to see some of that. So the example I've already shown from Corin Matthews' work, 10 divided by 2, there where the teacher began by saying draw 5 big circles, that we would code it as a problematic way, a problematic method for answering that question. So that would have been given a code 0. The other example I showed you earlier on, which we gave a code 1 to, was where a question like that, 10 plus 10 plus 10, is being answered by unit counting. Now, here's where in some ways things get interesting mathematically, because we have had people argue with us to say, well, you know, is that really a singular method? I could use unit counting for lots and lots of questions. In fact, I could use it for any whole number addition and subtraction I wanted to, and actually beyond into multiplication and division as well, if I wanted to. Now, that's where kind of our sense of being pragmatic applies, because we think that that method is local. In fact, we called it singular, because we think it generates the immediate answer in a very low number range. You know, sort of beyond grade 1, we wouldn't really want that method. And already ideally in grade 1, we would want some attention to number structure and properties. So that for us was a code 1. We had other examples, and here's another one, where and you've probably seen this one before. For example, when you multiply by 10, you write in a 0 to the number, would be with the kind of phrases that are used. And we gave that a code 2. Now, again, this is, we've had arguments about this within our team and beyond. We would call that a localized method, because obviously it works when you've got whole numbers and you're multiplying by whole numbers, but actually it's limited again. It's not generalizable for when we get beyond whole numbers into decimal numbers. So we wouldn't have coded that as a generalized method. It couldn't get a code 2. But in the early grades, we were giving a response like that. We would have given it a code 2, but not a code 3. And then we had examples like this, where teachers were using a jump strategy in this case, where we had teachers saying things like, remember, you've got to break your second addend. Now, often they didn't use the word second addend. They might have you break the second number in the addition down by place value, and you can then add in your head. So, for example, if I was doing 63 plus 25, you break the second number down by place value into 20 plus 5, and then in your head, you can add the 20 and add the 5. And we gave things like that a code 3, because that method, even if I did go into 3-digit numbers, whatever, I can still generalize. So responses like that, we were coding at a higher level. And that was some of the ways in which we were disaggregating the examples of teaching, the excerpts of teaching that we saw. So this strand, as we were sort of thinking about it and writing about it, in some ways it looks at the reach of procedures and explanations that are offered or validated by teachers. And I'll say a little bit more about the reach of procedures, because for us, it is an idea that leans quite a lot on variation theory. So underneath it for us, we were borrowing from Anne Watson and John Mason's work and their version of variation theory. And we were looking at quotes like this in their work, where in particular, there's the really nice constructs that I like of dimensions of possible variation and range of permissible change. And they talk about learning concepts in mathematics to become aware of aspects that can vary in examples while remaining as examples, and to become aware of over what range that change can take place. And this gives rise to the constructs of dimensions of possible variation and range of permissible change. Now, I think they're two lovely concepts. And in some ways, what we were doing was adapting them slightly to think about the range of the example space over which a method that the teacher was offering or an explanation that the teacher was offering can hold. Now, it's a slightly narrower reading, and we would acknowledge that it's a narrower reading. But why was that useful for us? In our formulation, because the focus is on the reach of a procedure, we're working on a ground where teachers see their job as teaching procedures. So in terms of building off the procedures and explanations, we're working with a teaching practice that is both familiar to the teachers that we were working with and is seen as core to the instructional work that they do. So this strand takes a practice that's familiar to teachers and overlays some developmental possibilities on that. And I'll say a little bit more about the developmental possibilities in a minute. But fundamentally, what we were doing was trying to expand repertoires within the existing classroom culture, rather than trying to overturn a classroom culture by insisting on something like a learner-centered pedagogy, for example. So what do we mean by using this idea, this kind of concept of the reach of procedures or the reach of explanations developmentally. We were doing quite a lot of work with primary teachers on developing their content knowledge and pedagogic content knowledge. And we ran a course at one point, a 20-day course with them. And in that course, we would give questions for the teachers to work on questions like this. So an example of a question that we worked on was, is -5 less than -8? And the question for the teacher was not just to answer that, but actually to say, what diagrams and explanations might you use to help you to explain your answer? And quite often with questions like that, we got two kinds of explanations, or two broad categories of explanations. One category, one group of explanations said something like -8 is less than -5 because -8 is further away from 0. And another category of explanations said, well, further to the left, the numbers are smaller, and further to the right, the numbers are bigger, and that's why -8 is less than -5. So that gave us some food for thought in terms of thinking about, well, how do we think about the quality of that explanation? So for us, mathematically, the first example, the reasoning in the first example, one way of thinking about that is problematic because the distance from 0 is not a critical feature for numerical comparison. But if instead, and the orientation we were taking to our work is that we are working developmentally, we could work with a variation theory approach. And again, for us coming from Anne Watson's work in particular, to say, well, okay, this is what you've said. Can you give me another example where that explanation works? And another one, and another one. And then go on to ask, well, does that explanation always work? Can you give me an example where that explanation wouldn't work? And another, and another. And getting towards, at the end of a cycle and a conversation and a discussion, where the focus would be on when does that explanation work and when does it not work. So starting to see, and again, I'm using Anne and John's work there, starting to see the boundaries of a procedure, of where the boundary examples are. So getting more skillful, getting more aware, getting more explicit about the procedures that they saw as central and fundamental to the work that they were doing. Another example that we saw, and this was a relatively unusual example, actually, in terms of a teacher who asked a relatively open-ended problem, and these are quite rare on the ground in South Africa. This was a middle grades teacher. It was a grade 5 class. And at the beginning of the lesson, she already had 3 number lines marked on the board. And you can see there you've got a 2 to 3 with some intervals marked, and a 7 to 8 with intervals marked, and a 4 to 5 with intervals marked. And her question to the class was, do you know how to count in these intervals? Can you tell me how you decide how we're going to count on these number lines in the intervals that I'd marked? And the class did some thinking, and they did come up with an answer to that question. The kinds of things that the children in the class were saying were, well, 3 spaces means thirds, 4 spaces means quarters, 6 spaces means sixths. Now they're already starting to grasp at generalized, at a kind of generality here. So this was interesting for us. And what it led back to me as I was observing this lesson was, well, thinking about the reach of the procedure that's just been offered by the children in this class, and doing a little bit of reverse mapping in terms of the dimensions of variation that the teacher has introduced and the range of permissible change here in terms of a conversation that we could then go back and have with the teacher. So that's what we then did. In terms of thinking about what varies across the examples that the teacher had offered, there was variation in the start and end numbers, and there was also variation in the number of equal intervals that she'd offered the children. What was invariant across her set of examples was that there was always a single unit in terms of the line segment. You had a gap of 1 in all the examples that we offered. So in terms of having a conversation with her about pushing on the children's teaching, we were then able to have a conversation with the teacher about maybe adding some examples that looked like this. So here's an example that kind of overtly looks quite similar to her examples, but this time you can see that the interval is no longer a unit interval. It's an interval which is 2 in the first instance and 4 in the second instance, and asking children now to think again about how they would decide how to count in these intervals on these number lines. And that was a nice conversation to be had, underpinned for us by variation ideas, and being able to be very explicit about that in our conversation with the teacher. So that's some of the developmental work that we were able to do in classrooms. So in terms of expanding the reach of procedures, what we were able to do over time was gradually increasing the reach of procedures and working with teachers on increasing the reach of the procedures in a context where the notion that mathematics is all about procedures is prevalent. So we could focus on this as an idea and use it for conversations with teachers. We could also start thinking about the example space in which the offered procedure holds and become more explicit about the contours of that space. And it's based on, for us, and we were able to kind of weave that into supporting teaching, which is moving towards and in a trajectory that's building towards structure and relation and generality, building on the connections that the teachers are able to make. So that was one avenue and one strand of the work that we were using, both for analysing teaching, but also for supporting teaching. Another strand, a second strand in the mediating primary maths framework, which again for us is underpinned by variation theory, was this idea about building mathematical connections. And I've shown you examples already of how we often see a very disconnected way of treating examples and working with them from scratch every time, rather than taking some examples as established, some results as established, and then building on those. So again, we had a coding here. And the coding began with, at the level 0, disconnected and or incoherent treatment of examples, or simply oral recitation with no additional teacher talk as well. So there were no connections in there. At level 1, we had the kind of example I showed you before, which is just every example treated from scratch. So examples themselves are coherent, but no connections are made between them. Building up from that, we had teacher talk that starts to connect between examples or between the artifacts or inscriptions used within across examples, or actually connecting between episodes. So the methods that are used in one episode is drawn into and used in a later episode in that lesson, or across lessons too. And at the top end, we were talking about teacher talk that makes vertical and horizontal or multiple connections between examples or artifacts and or inscriptions and or episodes. Now, underpinning that idea as a way of coding the quality of teaching, we were building on Annalena Ekdal's work, and in her earlier work in coding the work that she saw in South African classrooms, she distinguished between connections within examples that were made in some lessons and connections between examples. So that was a useful idea for us in terms of expanding the scope of connections that were being made. Underpinning that, there was Anne Watson's work, and early work that I really liked, where she talks about example spaces and working with the warp and the weft, which is the connections, that the ways in which structurally across equivalence often that things on one side of an equation or on one part of an example connects to another, and the ways in you can get vertical connections if you have a set of examples laid out in kind of a grid format. And in bringing in multiple representations of ideas across artifacts and inscriptions in our coding, we were also drawing on what Chinese variation theory tends to describe in terms of conceptual variation, which is seeing different instances of an idea across different contexts. So all of those were kind of built into the ways in which we were coding in this particular strand. And some examples of that were the example I talked about before, teachers working with pairs of numbers that add to 16 and dealing with every example separately. That would have been coded as coherent, level 1, but coherent, but every example treated from scratch. So it would have been a level 1 code here. And then another example, which Mike Askew wrote about in some of his later writing, was an example where a teacher works by decomposing numbers by place value. That all her examples are about decomposing numbers by place value. She includes 10 strips and unit squares with symbolic notation. She focuses on correctness of individual decompositions and patterns across the set in terms of numbers of tens, number, and units. And we had a question about whether this should be coded at level 2 or level 3. And I think Mike ended up by coding it at level 2 because he said, well, while there were some multidimensional connections, The examples and explanation was restricted always to 2-digit numbers, and there were no multiples of 10 included in the example space. So while there were connections, we didn't think it headed into the realm of generality here. So that's some of the ways in which we were thinking about and working with variation theory in the work that we were doing. The references are to be finished. I haven't done that yet. And then I'm done. So thank you, Forster.
Thank you very much, Professor Hansa. And I think we open the floor for questions, comments. So please, the floor is open. You can type in the chat and then we will read. So,
okay, I can see Ulla's question. Misunderstanding to say, I think variation is restricted to certain topics. Apply and make use of in certain topics. Ulla, can you say a little bit more about that?
Yeah, that was a comment to a discussion we had before.
Oh, earlier on, sorry.
Thank you.
My apologies.
so maybe Professor Hamza, while we are waiting for questions, if you have any thoughts that you may want to share. Okay, we have a first question. Is it that effective for mathematics in higher classes? So basically, can VT be applied at tertiary level, high school level?
I think it can. And in fact, much of the early work on variation theory I was reading was coming from actually secondary. So I actually came across, well, to be fair, the first work that I read, because it was learning and awareness, had been done in the context of early number working. But actually a load of Anne and John's work and some of the Swedish work that I was reading was actually coming from secondary level maths. So I was actually worried about whether we could take it the other way and go downwards back into primary level, and whether it was useful beyond very early number learning, which is what Dagmar Neumann had written about, which is what was reported in Learning and Awareness in the book. So yeah, absolutely. There are lots of examples of using variation theory at secondary level and in tertiary as well.
Can I second that about tertiary? To me, it applies whenever you're thinking about teaching something to people, to ask yourself what are the critical ideas and what's the variation that will expose that. And it almost,
to me, I know phenomenography and variation theory have been done in a number of subject areas, and Ulla will know a load about this because the Swedish work has done a lot of this. I find it almost archetypally useful for mathematics. It's almost so fundamental to the ways in which I think mathematically that it was just such a natural fit for mathematical thinking and working.
That's what I'm going to be talking about in the last session.
I'll be there on time for that one, John, I promise.
Let's see.
A question about commercial maths. I don't understand the question.
Yes, I've asked him to unmute so he can explain further. So yes, please go ahead. The individual who asked the question about commercial math, please go ahead and explain further.
Good evening, everyone. Good evening, everyone.
Hello.
Hello, ma'am. I'm from Lucknow, India. My question was like, sometimes it is not that effective for the topics if I take compound interest, simple interest, or maybe profit loss. For pictorial presentation, of course, like for geometrical part, if we say, it is quite effective, but not for the commercial maths, as we say about like percentage, though it is, their examples are there for percentage, but for compound interest, simple interest, very few examples are there. And today I was looking for circles also, even I did not get up to the level of children I was trying to find in variation theory.
I think, and Ulla, you can correct me here, one of the earliest papers I read was about commercial mathematics. It was certainly about ideas within economics. I'm not sure it was a maths education paper, but I've certainly read.
Yeah.
And I think we can probably point you to some of those studies.
Yes, the study you're talking about, Hamza, is about the conception of price and how improve secondary students' conception about price of demand and supply. So this is an example of how you can design a lesson that enables the students to see the relation between supply and demand. And I think that I can see that in the fact there are a lot of questions about if this is applicable in different topics. And I want to say this again. This is a general idea about how we learn. We learn by seeing differences. We learn by seeing how things are related to parts and wholes. And we learn, and I usually take, if I may take a very specific example about some people are very good at differentiating and know a lot about wines. And how do they learn that? They don't learn that by tasting the same wine thousands of times, but by tasting wines that are different. And even Maria Montessori used this idea when she was working with children, disabled children, mentally disabled children. And in her material, if you are familiar with that, she starts with very big contrasts and progress this variation and narrowing the contrast so they can see nuances. And I think this is a very excellent example of that. Learning by seeing variations, seeing differences is a general thing. And this idea is something we can use whatever subject we teach, whether it's history, whether it's language, because there are a lot of studies made and published in how to learn Chinese, for instance, especially in that book that you had on your first slide, one of your first slides, Hamza.
Yes.
And I agree that it is maybe more easy to apply on mathematics due to the very parent structure that is within that can be seen in mathematics. But I want to say it again. This is a general idea about how we learn. So I think as I said in chat, I think it is a misunderstanding if you think this is something that has to do with certain topics in mathematics.
Yeah. May I say something about the commercial arithmetic? The example that you gave was about simple interest and compound interest. Well, that seems to me to cry out for comparison, to look at the effect of simple interest on an investment and the effect of compound interest on an investment, and to alerts you to thinking, why is this? What is the difference? If I'm saying it's 10%, why isn't it the same? And then to look at how the 10% works with simple interest in year 1, year 2, year 3, and how the 10% works in compound interest in year 1, year 2, year 3, and that the percentage is being applied to something different in compound interest than it is in simple interest. So that intrigues the learner. Why are these things different? Well, because there's something different going on. What is it that's different that's going on? And then if you take it, if you don't vary the rate of interest, and you don't vary the initial capital, what's it called, the principal. If you keep those things the same, then you can see that simple and compound interest are different. You're using variation to draw attention to the essential difference. Now, when it comes to working out the 10%, that's something which has happened, a long time before. So, yeah.
There's also, for me, an interesting critical aspect here, which is that percentages mean nothing until you say percentage of what. And that comes out in this example.
Yes.
Yeah.
Professor Hamza, I think there's a last question from Lee.
Yeah.
Yes. Is it the one in the chat?
Yes, please.
So there's and the question is about whether we were explicit with the teachers that we were working with variation theory, and whether we introduced them to the theory in any way. So I think here it's one of the ways in which we might differ from the ways in which I've read about learning studies, where I think they are very explicitly underpinned by variation theory in terms of the process. We did not use the language, the kind of the academic language of variation theory in terms. So we didn't talk about dimensions of possible variation, reach of permissible change, the range of permissible change. We weren't using that kind of language with the teachers. We were using the language of what varies and what stays the same. So those kinds of questions were used. So in some ways, it was the translation of variation theory into a language which we thought would be accessible to primary teachers, rather than an explicit sharing of the theory. Does that make sense?
Mm.
And it's a choice. I mean, I in many ways, I think if we'd had the time to do a more in-depth course, I think it would be very nice to actually get teachers into understanding the formal concepts in some way, and then learning to use them. But I think it's again tied to the terms of that course. It had to be pragmatic interventions that could go to scale. And we didn't think that jumping in with, we wouldn't have had the time anyway, the length to actually work over time and get into those concepts. But absolutely, I think they're useful for teachers to know about.
Yeah, and my experience is that you can sort of interweave these theoretical concepts while you are practically working with designing examples, for example. And I think the advantage of implementing these concepts, variation, invariance, and contrast and things like that, is that the teachers, we have found that the teachers develop a common professional language. They have a language to talk about when they talk about their teaching, and I think that is something very important. But we don't have courses and then I start to do it, so we do it more integrated in the work while we are working with the teachers.
Yeah.
Okay. So Professor Watson, Professor Mason, Professor Davis, maybe any final thoughts since you started the part one before we bring an end to today's session? Any final thoughts? Okay.
My only thought is,
Good.
wow.
Yes, go ahead.
Thank you, Hamza.
Thank you.
Thank you, John and Forster. My apologies again.
Yeah.
No, it was worth the wait, and we want to thank you sincerely for making time to share your body of research with us, and we look forward to learning from you and also hearing from you in other sessions.
Well, I'm
And
looking forward to the next couple of lectures as well. So thank you very much for organizing.
You're welcome. By way of announcement, please, we got to hear from our next speaker briefly. So on December 6th, we will have our 5th session in this VT series. Professor Brent Davis and then Professor Martina Metz. We look forward to seeing us all and more people joining. And the time remains 3 p.m. GMT. And you enjoy the rest of your day. Those who are getting ready to sleep, we hope that you have a wonderful sleep. And those still working, enjoy the rest of the day. Thank you once again and see you on the 6th.
Thank you.
See you. Bye-bye.
Bye.
Bye.